Here's a review for Unit 8 gas laws. I'll go through and do these problems with you and answer questions so that you're prepared for the Unit 8 test. Under what conditions do real gases not obey the ideal gas law? They get further and further away from actually obeying the ideal gas law, or that pressure times volume is equal to the number of moles times the gas constant times the temperature. Things get further and further from ideal at high pressures, and in addition to high pressures, low temperatures. Because under high pressure, the gases are crunched closer together generally, and in addition, at low temperatures, they're moving a little bit slower, and so they're more likely to actually behave more real instead of ideal. So it's just a continuum. There's no absolute cutoff, but generally the higher you get the pressure, the lower you get the temperature, the more real it behaves, or not ideal. And ideal behavior improves, vice versa. More ideal is at lower pressures where they're not so crunched in together, and at higher temperatures where they're moving very quickly. By raising the temperature of a gas in a fixed volume container, that word fixed means you've got some sort of hard container like a metal tank. Does the pressure increase or decrease? So if the volume is the same, and you're looking at a pressure situation, essentially what we've got is P1, V1, T1, or combined gas law, P2, V2, T2. Fixed volume means you can take out the volume, and we're looking at P1 over T1, P2 over T2. This would be Gay-Lussac's law. And raising the temperature, when two things are in one ratio like this, then you're looking at them being proportional or directly related to each other. So raising the temperature is going to increase the pressure. If the amount and temperature of a gas are kept constant, so no extra gas and the temperature is the same, what happens to the volume when the pressure is increased? Again, P1, V1, T1 is equal to P2, V2, T2. Temperature is kept constant, so we're looking at a Boyle's law or inverse relationship. When two things are next to each other in a proportion, that means that they have an inverse relationship. As one goes up, the other one goes down. So since pressure is increasing, then our volume is going to decrease. When a gas is kept constant, it's kept at constant pressure, does the temperature increase or decrease when the volume is decreased? One more time, let's see, P1, V1, T1, P2, V2, T2. This time we've got a constant pressure, so we're looking at a direct relationship. As one goes up, the other one also goes up. As one goes down, the other one would go down. So the volume decrease would result in a temperature decrease also. What happens to the density of the sample if the volume is increased? So for density of gases, density is still equal to mass divided by volume, even for gases. So if you take a sample and you increase its volume, that means you're increasing the denominator. With the same number of particles in there, the mass is the same. Increasing the size of the denominator is going to make the density go down. Your density is going to decrease. That's just what happens mathematically. If your denominator gets bigger, it makes this whole value get smaller, so your density is going to go down. The pressure of a mixture of gases is 600 kilopascals. If nitrogen molecules are 4 times the number of hydrogen molecules, oxygen molecules 3 times the number of hydrogen, and carbon dioxide molecules are 4 times the number of hydrogen molecules. What are the partial pressures of the gases? Okay, so we know the whole thing is 600 kilopascals. Let's think through this. And that's going to be equal to all of the individual pressures added together. So nitrogen is 4 times the number of hydrogen. The pressure that a gas exerts is directly related to how many particles there are in the mixture. So let's see. So nitrogen is 4 times the number, so 4 times hydrogen's value. Oxygen, 3 times hydrogen's value. Carbon dioxide is also 4 times hydrogen's value. And then hydrogen. So 4 plus 3 plus 4 plus 1, we've got 7, 8, 12. So 600 is equal to 12 times hydrogen's value. So we're going to divide both sides by 12, and let's see, it looks like that's going to be 50. Let me double check with my calculator. 600 divided by 12 is equal to, yes, that was right, 50. So hydrogen is 50 atmospheres, or kilopascals, I'm sorry. So hydrogen is 50 kilopascals. Then, let's see, what was the order? Nitrogens must be 4 times 50, or 200 kilopascals. The oxygen was 3 times, so 3 times 50 is 150 kilopascals, and carbon dioxide is also 4 times, or 200. So it turned out that that total pressure was broken down into 200, 150, 250 kilopascals, which does indeed add up to our 600, so that works out. An enclosed container has a pressure at 84. What is the new temperature if the pressure is lowered? So we're talking about a change. Change means P1, the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. Pressure, temperature, enclosed container. It doesn't say anything about the volume. It must be a container that is going to keep a constant volume. So we essentially have our combined gas law simplified down to P1 over T1 equals P2 over V2. I'm pretty sure that's Gay-Lussac. So what is the new temperature? So we're solving for T2. When we solve for T2, then what we need to do is get it out of the denominator. For a lot of people, the easiest way to solve that is to do a cross multiplying. P1 T2 is equal to P2 T1, and then divide by P1. The thing you have to make sure of is that that T2 gets out of the denominator, and that can confuse people sometimes. So it turns out that the second temperature is equal to the old pressure, TP. Remember, solve for what you need before you try to put numbers in. So our new temperature is going to be equal to the new pressure. P2 means the new pressure. So the new pressure is 210 kilopascals. And let's see, T1, the original temperature was 84 degrees. Okay, I just had to shut my door. 84 degrees with 273 added to it to convert to Kelvin. We don't need to worry about the decimals because 84 doesn't have any decimal places anyway. So 273 plus 84 is equal to 357 Kelvin, divided by P1. The original pressure was 460 kilopascals, and units work. The kilopascals cancel. We're left with Kelvin, which is what we should have gotten. So let's see, that 357 times the 201 divided by the 460, and let's see, how many significant figures can we have? We can only have 2 for all of this. So our new temperature is going to be, the calculator reads 155.9934783, but we're going to have to call it 160, and that's why, because of significant figures, kilopascals. So there's our final answer. Next question. At conditions, okay, here's the pressure, here's the temperature, gas occupies a certain volume. What will be the temperature of the same gas? We've got a new pressure and we have a new volume. So we're going to use the complete combined gas law equation. P1 V1 T1 equals P2 V2 T2. Nothing's getting crossed out because we have 2 changes. What will be the temperature of the same gas? So we're solving for T2, new temperature. Again, to solve for that temperature there in the denominator, for a lot of people I've discovered, they kind of like the idea of cross multiplying and then dividing. Whatever way algebraically works for you is fine. I've just found that people like seeing it this way, ones who are confused anyway. If you're not confused, do whatever works for you. But if you are confused, cross multiply and then divide off what you don't want. The cross multiplying essentially gets rid of anything in the denominator. So those are now gone, and it turns out that the new temperature is going to be equal to this. Not going to try to read it all off too clunky. New pressure, P2 means the new pressure. The new pressure is 2.43 atmospheres ATM. The new volume, V2 means the new volume, 41.6 liters. And the original temperature, T1 means the original, 22.6, 22.6, I'm going to add to it 273.2. I'm going to use that decimal place, 295.8. Kelvin. It's not looking real pretty. It's supposed to be 295.8 Kelvin, but whatever. P1, the original pressure, 4.73 atmospheres. And V1, the original volume, 32.8 liters. Cancel, 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 and we're left with degree Kelvin, which is what we're supposed to have. And then you just do all the math. 295.8, I have that in my calculator screen, so I'm going to put that in first, times 41.6 times 2.43, then I'm going to go ahead and just press enter and get it over with. Then I'm going to divide by 4.73, I'm going to press enter again, why not? And then I'm going to divide by 32.8, and there's 192.7359769. We can use, it looks like 3 significant figures, and so 193. Our new temperature, where are we going to put it? I guess my T2 is equal to 193 Kelvin. Number 9, what volume will 4.93 grams occupy at this pressure and this temperature? There's no change this time. We're not doing P1, V1, T1 anymore. We're doing PV equals N, R, T. How do we know? There's no change. There's not two of anything. We just simply don't know the volume. So that's our ideal gas law. Remember, the ideal gas law works out best when the temperatures are high and the pressure is low. So volume, we need to solve for V, so we're going to take this side and divide by P, this side and divide by P. So volume is going to be equal to the number of moles times the R constant times T divided by P. We don't have moles, but we have grams. That's the same thing. You should be very comfortable with that since way back in Unit 6. 4.93 grams of carbon dioxide. Let's see. 4.93 grams divided by the molar mass of carbon dioxide, I think, is 44.01. So divided by 44.01 is equal to, so our number of moles here is 0.112 moles. R value, which one are we going to use? We have a few to choose from. We're going to use the one that's got millimeters of mercury or torr, and that R value is 760. I'm sorry, I said that wrong. It is 62.4 liters times millimeters of mercury. I know working with all these units is a little clunky, but it's really, really good practice for you. Per mole degree Kelvin. And see, the temperature is already in Kelvin, so don't add 273 again, it's already there. 305 Kelvin, lastly divided by the pressure, which is 820 millimeters of mercury. Your pressure units, you're fine. There's an R value for just about everything, so you don't have to worry about it. The mole cancels with the mole. Those cancel, and even these cancel, and we should be left with just liters not canceled, and we are. Here it is. Then mathematically, we take the calculator and we multiply by 62.4, and we also multiply by 305, enter, divided by 820, and we can use 3 significant figures, so 2.60 liters. 2.6, I'm supposed to read 60 liters is our new volume. Let's think about it. Okay, yeah, that makes sense. 262, yeah. One more, are we done? Are we to the bottom of the sheet? It seemed to go pretty fast. What is the density of 6.55 grams of oxygen gas at 34 degrees Celsius and that many atmospheres? So for density is equal to mass divided by volume. We already have the mass that gave it to us. But what we don't have is the volume, so we have to go find it ourselves with PV equals nRT. So PV equals nRT is just a tool, really, to solve for the volume so that we can then, second step, find the density. So it's a two-step problem instead of just a one-stepper. Our volume is going to be equal to our number of moles, so we have to convert that 6.55 grams. So 6.55 grams divided by 32. Don't forget oxygen is diatomic. It's not 16, it's 32. So our number of moles here is 0.2204. I guess I'll call that 5. That should be enough significant figures to work with. Moles. Which R value are we going to use? The one that is with atmosphere, so 0.0821 liter atmosphere mole degree Kelvin. Temperature. Our temperature is 34. I'm going to add 273 to it. So 273 plus 34 is equal to 307. And that's in Kelvin. And then lastly, divided by the pressure, which is 0.67 atmospheres. I know the temptation is strong to avoid the units. I get it, but it's so useful to hang in there and actually use them because it can be a check. If you forgot that you had to use the one with atmospheres, for example, that would be a moment right now where you'd be like, whoops, wrong R value. Then we're going to solve for our volume. So 307 times 0.082 times 0.205, enter, divided by 0.67. And our volume ends up coming out to be 7.7 liters. So now we can go over here with our density and get 6.55 grams divided by the 7.7 liters. And the density of our gas is 6.55 divided by 7.7, or 0.85 grams per liter. The units of density are in unit of mass divided by unit of volume. They don't have to be any particular ones, so we're good. Now I think that wraps up the sheet, so let me end this.